Good morning, students. In the last lecture, we discussed about the composition of two SHM. Means when two SHM combine with each other, what is the resultant wave, or what is the resultant motion, and what is the resultant amplitude, what is the resultant initial phase. We discussed it in our earlier lecture. Today we are going to discuss another very important topic in this chapter, which is nothing but the energy of a particle performing simple harmonic motion. Now we know that simple harmonic motion is nothing but the motion of an object which perform or which is always directed towards the mean position, and the force is always proportional to the displacement of the particle. Now energy of particle performing SHM, in which what is this energy? This energy is nothing but the total energy of a particle performing SHM at a particular point, particular position. So when this motion is performing, the particle is performing the simple harmonic motion, it traveling from extreme position to the mean position and mean position to the extreme position. This process continues, and we can say that every time it changes its position, its velocity also get changed. So due to its velocity, it possesses the kinetic energy. So the kinetic energy of the simple harmonic motion, kinetic energy of a particle performing simple harmonic motion is due to the velocity of a particle performing SHM. Its velocity is different at different points. We know that velocity at the mean position is maximum and the velocity at the extreme positions are zero. So we can say that the velocity changes, therefore the kinetic also changes. So this kinetic energy is due to the speed of the particle. And how we get the potential energy? Potential energy is due to the position of the particle performing simple harmonic motion. As we know that as the time changes, it changes its position, therefore the potential energy of a particle performing simple harmonic motion also get changed. So there is a change in kinetic energy as well as there is a change in the potential energy. So here we are going to derive a simple relation for the total energy of a particle performing simple harmonic motion. We are starting from the kinetic energy of a particle. We know that what is the kinetic energy? The kinetic energy is given by 1 by 2 mv square. This is the simple relation of the kinetic energy, where this v is the velocity of the particle. But we have already derived a relation for the velocity of a particle performing simple harmonic motion. What is this relation? This relation is this velocity is equal to omega under root a square minus x square. Okay, so therefore this kinetic energy is equal to what? It is equal to 1 by 2 m omega square a square minus. This is the simple relation. Okay, this is the simple relation for the kinetic energy of a particle performing simple harmonic motion. Now here we can replace this m omega square by k. This k in bracket a square minus x square, where this k is nothing but the force constant. Okay, so this is the kinetic energy of a particle performing simple harmonic motion. So this is the kinetic energy. Now we are moving towards the potential energy. So how can we calculate the potential energy of the particle performing simple harmonic motion? It can be calculated by using a simple relation, that is dW is equal to F multiplied by dx. Okay, consider here a particle is performing simple harmonic motion, and if the particle is to cover a small distance dx against the restoring force F, then there must be some work done. Okay, what happening? The force is acting on this particle, and the force is always directed towards the mean position. Okay, means we can say that the direction of force like this, and the displacement is like this. So this F and this dx, they are oppositely directed to each other. So in this case, to travel this distance dx opposing the force F, some work must be done, and this work is equal to, so we can write here the work dW is equal to minus F into dx. What this minus sign indicate? This minus sign indicate that this force and displacement, they are oppositely directed. Now we already know what? We know that this force is equal to minus of kx. In the simple harmonic motion, this force is oppositely directed to x. Therefore, we can write this F is equal to minus of k into x, where this k is again a force constant. So we can write here this dW is equal to, this minus minus get plus, it is equal to kx multiplied by dx. What is this dW? This dW is the amount of work done to cover a displacement equal to dx. If we need to calculate the potential energy or total work done, we need to integrate this equation. So the total work done W is equal to this integration of dW. Okay, so we can write here, which is equal to, it is equal to k into x into dx. Now which is equal to, this k is a constant, so we are taking out of the integration sign, this k into integration of x multiplied by dx, which is equal to k into x square divided by 2. So we can write this W or the work done is equal to 1 by 2 k into x square. So this is the work done, and this work done is stored in the form of potential energy in the simple harmonic motion. If there is a magnet, then it is a magnetic potential energy. If there is a simple pendulum, it is a gravitational potential energy. In the case of this simple harmonic motion, this work done is stored in the form of potential energy, and this potential energy is equal to 1 by 2 k into x square. Okay, so this is potential energy of a particle performing simple harmonic motion. Now, what is total energy? Total energy is the sum of kinetic energy and the potential energy. So we can write here total energy is equal to kinetic energy plus potential energy. So it is equal to, what is kinetic energy? It is 1 by 2 k a square minus x square plus 1 by 2 k into x square. If we simplify this equation, we get 1 by 2 k a square. This is the total energy of a particle performing simple harmonic motion. So, in this case, we derive a simple relation for the total energy of a particle performing simple harmonic motion. As we know that the total energy of any system remains conserved, we can say that the potential energy can be converted into kinetic energy. This kinetic energy can be converted into potential energy, but the total, the sum of the energies, that is the total energy, always remains conserved. It remains constant, which is equal to 1 by 2 ka square, where this a is nothing but the amplitude of the simple harmonic motion. If we keep this k is equal to m omega square and a square. So this is another relation for the total energy, which is equal to 1 by 2 m omega square a square. Okay, so this is the relation. This relation also can be modified by keeping the value of omega. What is omega is equal to? This omega is equal to 2 pi by t. So this equation also written as total energy is equal to 1 by 2 m into 4 pi square by t multiplied by a square. Okay, this is the example divided by what? This t square. So this is the another relation for the total energy. So we derive the relation for the total energy of a particle performing simple harmonic motion. Now we are going to discuss some special cases according to the with the concern of the energy, this total energy of the particle performing simple harmonic motion. So what are the cases? So first of all, we are going to write all these three equations. So what is the kinetic energy? This kinetic energy is equal to 1 by 2 k a square minus x square. Potential energy is equal to 1 by 2 k into x square, and this total energy is equal to 1 by 2 k. So we are going to take some special cases. Case 1, when the particle is at mean position. When the particle is at the mean position. What are the properties of mean position? At the mean position, x equal to 0, that is the displacement is equal to 0, because we measure the displacement from the mean position. So in this case, mean position, this x is equal to 0. Then what is the kinetic energy at the mean position? is equal to 1 by 2 k a square. Okay, because this x equal to 0, we are going to omit this x square. So kinetic energy at the mean position is equal to 1 by 2 k a square. Potential energy at the mean position, as this potential energy is totally depend upon the displacement, and the displacement is equal to 0 at the mean position. So this potential energy at the mean position is always equal to 0. Then what is the total energy? The total energy at the mean is equal to sum. It is equal to 1 by 2 k e. So this is the total energy at the mean position. Now we are going to take another case when the particle is at the extreme position. H2 at the extreme position. So at extreme position, this x is equal to a. So then what is the kinetic energy at extreme position? It is equal to, as x is equal to a, we can replace this a with x. So x square minus x square is equal to 0. Therefore this kinetic energy is equal to 0. What is the potential energy at the extreme position? Now this x is equal to a. So we can keep this x is equal to a. So it becomes 1 by 2 k square. Then what is the total energy? Total energy at the extreme position is equal to 1 by 2 k. So we can see that the total energy at the mean position is equal to total energy at the extreme position, which is equal to the total energy at any position. So during the simple harmonic motion, the total energy of the simple harmonic motion or the particle performing Shm remains constant. Okay, so this is the simple cases in which we show that the energy is conserved in the case of simple harmonic motion. Now this can be explained on the basis of a very simple graph. This graph is like this. See here. So by using this graph, we can explain these two cases at mean position and extreme position. So this is the simple harmonic motion in which this is the mean position and these two are the extreme position. This is left extreme position and this is the right extreme position. So during the simple harmonic motion, when the particle at the mean position, when the particle is at the mean position, what happens? At the mean position, this kinetic energy is equal to 1 by 2 k square, which is equal to the total energy. So we can write at the mean position the kinetic energy is equal to the total energy. Potential energy is equal to 0. We have first draw the graph of potential energy at the mean position is equal to 0, so this is the potential energy. In the case of extreme position, this potential energy is maximum, here maximum, here maximum. So the graph is like this. This is called the potential energy. As we observe, there are two such points, this point and this point, at which the kinetic energy is equal to the potential energy. So as the kinetic energy increases, potential energy decreases and vice versa. So these cases can be explained with the help of this simple graph. Okay, so this is for today, and we explain here the energy of particle performing SHM for the potential energy, kinetic energy, total energy, and simple cases and a simple graph. So this is for today. Have a good day. Bye.